Compressed air is used in thousands of different applications worldwide. The quality of the air delivered to each application can be as varied as the applications themselves. The International Standards Organization, ISO, a worldwide federation of national standards bodies, has categorized the quality of air into classes and has defined the contaminants that can affect air quality. These contaminants include solids, such as dirt, dust, wear particles, and pipe scale. Water, that is present in the atmospheric air as a vapor. Oil, either in liquid or vapor state. Contaminants can come from a variety of different sources. Some contaminants come from the ambient air through the compressor intake. These include dirt and dust, water vapor, hydrocarbon vapors, carbon monoxide, and many other gaseous vapors that may be in the area. Contaminants can come from inside the compressor. Oil aerosols and vapors are an oil carryover, and there can also be solid wear particles, such as metal and Teflon particles. Finally, contaminants can come from the air distribution system itself. These include rust in pipe scale and desiccant dust from dryers. Contaminants in compressed air adversely affect all components of the air distribution system and can increase the pressure drop, costing you money. Wet, dirty compressed air can rob your system of usable capacity. Water in the system can cause airlines to rust and leak. With water present, the power and efficiency of air tools decrease. Water can wash out protective lubricant and tools and can even cause pipes to break in freezing conditions. Dirty air can be costly because it contributes to product rejects. Water and oil in the air affect paint spraying and other applications. Oil carryover not only causes damage to the final product, but can be a health hazard if untreated or disposed of improperly. Contaminants can cause spoilage in food processing and pharmaceutical applications. Solid particles in the airstream abrade wear surfaces. This increases your maintenance and repair expenses. When contaminants collect in an air system, they can collect on the surfaces of pipes and fittings, causing expensive pressure drops. With the proper air treatment equipment, system power is maintained, operating expenses and downtime is reduced, and production quality is improved. But how much should air be treated? To help you determine how much to clean your air, refer to the guidelines set out by the ISO standard 8573. They allow you to specify the air quality you need for your particular applications, and they help the air treatment manufacturer choose the proper equipment to obtain the air quality required. There are three basic steps in the treatment of air. They are cooling, drying, and cleaning. Air leaving a compressor can be very hot. Aftercoolers reduce the temperature of the compressed air to safe, usable levels. They also precondition the air for further treatment. In a water-cooled aftercooler, water between 60 and 90 degrees Fahrenheit flows around a tube bundle that carries the compressed air. An air-cooled aftercooler uses a fan to blow ambient air against a radiator-type heat exchanger, in which the hot compressed air travels. Water is the most common contaminant in an air system, since all atmospheric air contains water vapor. This vapor will condense into liquid water in the compressed air system if it cools down past the dew point, which is the temperature at which a vapor turns into a liquid. Anytime the temperature of the compressed air drops below the dew point, moisture will drop out of the air. It's important to manage where the water drops out in your system so that it does not affect your end product or system components. A 100 CFM compressor at 100 psig on a 75-degree day with 75% relative humidity will produce 18 gallons of condensate in a 24-hour period. A 500 CFM compressor will produce 96 gallons of condensate. With the controlled cooling of the hot air discharged from the compressor, water in the air system can be managed. Pressure also affects the air's dew point. As air is compressed, the pressure rises and the air is able to hold less moisture. In fact, a large amount of water would drop out of the air in an air compressor if it weren't for the fact that as air is compressed, its temperature also increases. The warmer the air, the more vapor it can hold. For every 20-degree Fahrenheit rise in temperature, the water-holding capability of air doubles. The inverse is also true. The cooler the air, the less water vapor it can hold. As air cools, the vapor condenses into a liquid. Air at 80 degrees Fahrenheit can only hold half as much water vapor as air at 100 degrees Fahrenheit. An aftercooler will remove about 2/3 of the water in your system, simply by cooling the air and using a water separator and drain to remove the liquid. It's important to use a reliable drain system to prevent condensed water from damaging downstream equipment and product. When the compressed air leaves an aftercooler, it is 100% saturated, meaning it cannot hold any more water vapor. At this point, the relative humidity is 100%. Relative humidity is the amount of moisture that is present in the air compared to the total amount of moisture that air can hold. When this vapor-laden compressed air enters downstream piping and cools even further to a temperature below the dew point, more of the vapor will turn into a troublesome liquid. But by drying the air before it travels downstream, that moisture can be removed from the system. How dry should your air be? You should specify a dew point lower than the lowest ambient temperature the compressed air system is exposed to. Remember to consider the air lines located in unheated areas, in front of open doors or windows, between buildings, or underground. System operating pressure is also critical in specifying the correct type of drying equipment, because the moisture load, or inlet air dew point of the drying equipment, varies inversely to the operating pressure. The higher the pressure, the smaller the dryer needed. Different applications require various grades or classes of compressed air quality. Use the ISO guidelines to choose your drying equipment. There are several ways to dry the air. The most common way to dry compressed air is by refrigeration. Here's how air is dried in a refrigerated dryer. Hot compressed air enters an air-to-air heat exchanger where it is pre-cooled by the chilled outgoing air. Pre-cooling the incoming air removes approximately 1/2 of the heat load, allowing the use of a smaller, more economical refrigeration condensing unit. Air then enters the air-to-refrigerant heat exchanger where it is cooled to the desired dew point temperature. As the air cools, water vapor condenses into liquid droplets. Air and the entrained water enter a separator where the liquid water is removed from the airstream. The collected water is discharged from the separator by a drain. Dried, chilled air passes through the secondary side of the air-to-air heat exchanger, where it is reheated by the incoming hot air before it exits the dryer. Reheating the air does not change the dew point of the air, but it does increase its effective volume, which enables it to do more work. It also prevents pipe sweating downstream. Refrigerated dryers provide pressure dew points from 38 to 50 degrees Fahrenheit. As long as the compressed air in the system is not exposed to temperatures below the dew point temperature or contaminated with any wet air, the remaining water vapor will not condense in the airstream. Deliquescent dryers obtain a dew point of 10 to 50 degrees Fahrenheit below the temperature of the inlet air. They do this through absorption. In this process, compressed air passes through a tower filled with deliquescent material, such as water-soluble salt and inorganic compounds. As this material absorbs the water vapor, it dissolves into a liquid substance and then is drained from the dryer. Absorption continues until the material is completely dissolved, at which time it must be replenished, which is usually a couple of times a year. Regenerative, or desiccant dryers, provide pressure dew point temperatures of 40 degrees Fahrenheit below zero to 100 degrees Fahrenheit below zero. They do this through adsorption. With adsorption, the water vapor is attracted to solid, highly porous surfaces called desiccant. Examples of desiccant include activated alumina and silica gel. Regenerative dryers consist of 2 adjacent desiccant towers or tanks. Compressed air passes through one of the towers with the desiccant material. While adsorption occurs in this tower, the desiccant bed in the other tower is being dried or regenerated. On a heatless regenerative dryer, this drying happens when a purge stream of the previously dried air passes over the saturated desiccant. Because the air is super dry, the moisture on the desiccant evaporates into this purge air, which then exits through a muffler to atmosphere. Heated type regenerative dryers use a heat source to reduce the amount of purge air needed to dry the desiccant beads. Membrane dryers provide dew points between 40 degrees Fahrenheit to 40 degrees below 0 Fahrenheit. This process works through selective permeation through a membrane to separate water vapor from compressed air. Water vapor diffuses through the semi-permeable membrane walls while the dried air continues downstream. A small portion of the dried air is redirected to be used as sweep air to remove the water vapor from the outside of the membrane shell. It costs money to operate any compressed air dryer. Every dryer has a pressure drop across it. In the case of the refrigerant type, the dryer uses electricity to operate. In the case of the desiccant and membrane type dryers, an amount of purge air is required to dry the desiccant. This can be up to 15% or more of the capacity rating of the dryer, depending on the desired dew point. Finally, in regenerative and deliquescent dryers, the desiccant must be periodically replaced. Each dryer has distinct advantages and disadvantages. Refer to the Compressed Air and Gas Handbook for more details. Remember, to reduce operating costs, do not dry the compressed air to a dew point below what is needed for your specific application. We've showed how the air is cooled and dried. Now, let's see how it's cleaned. Cleaning the air starts at the very beginning of the process. An air filter is used to filter dust and particulate coming into the compressor. Filtration is also needed to remove contaminants that come from the compressor package itself and the compressed air distribution system. Selecting the proper filtration depends upon the degree of filtration required, the allowable pressure drop, and the filter life expectancy. Every filter has a pressure drop across it, and this generally increases over time as the filter does the work of cleaning the compressed air. Use the correct type of filter or filters to achieve only the level of cleanliness required for specific applications. Filters are rated by the smallest particles they are able to capture. Absolute rating means the removal of all particles of a certain size. Once again, use the ISO guidelines to choose your filtration equipment. Coalescing filters remove contaminants such as aerosols of water and oil from an airstream by causing them to unite, or coalesce, into droplets. Droplets combine until there's enough mass to gravitate to the bottom of the filter cartridge, where it must be removed by a reliable drain. Oil in the compressed air system is a contaminant and can be hazardous. A coalescing filter is recommended before any dryer whose drying medium may be damaged by oil. Mechanical separators use centrifugal force to separate liquid droplets from the airstream. Particulate filters can be either of two types, a surface filter or in-depth filter. A surface filter uses a screen or sieve to trap particles. In-depth filters contain a bed of randomly positioned fibers. Particles are captured throughout the bed as they make their way through the medium. Particulate filters are recommended immediately downstream from a regenerative and deliquescent type air dryer to catch any desiccant dust. They are also used to remove pipe scale and particles that come from the compressor package. Selective applications, such as food processing and breathing air, require the use of an oil vapor filter. An oil vapor filter works by adsorbing oil vapor onto the surface of activated carbon. Activated carbon has a selective preference for oil vapor over water vapor. When needed, oil vapor filters are commonly installed downstream from a coalescing filter. Not all air should be treated the same in a compressed air system. In fact, your operating expenses will increase unnecessarily if you overclean your air. Anytime compressed air goes through air treatment equipment, there will be a drop in pressure. Also, the more air treatment equipment there is, the more maintenance hours will be required to service it. It's not unusual to find different air quality requirements in the same air system. What do you do in this instance? Well, a suggestion would be to place the air treatment equipment closest to the point of use requiring it. This way, only the air needing special treatment is treated, while the rest of the air system receives the treatment it requires with the minimal amount of pressure drop. Maintenance plays a key role in the efficiency and quality of a compressed air system. Filters that are not maintained can result in costly pressure drops, creating an artificial demand and requiring compressors to operate at higher pressures. Filters should be maintained regularly. To assist maintenance personnel, be sure to install bypass valves around every piece of air treatment equipment. This allows service to be done at any time. Since some contaminants do come from the atmospheric air, consideration should be considered when choosing a location for your air compressor. Locate the compressor in a cool, clean, and dry, uncontaminated area. Avoid nearby painting, chemical cleaning, or engine exhaust. The area should be free from corrosive fumes such as chlorine and ammonia. The compressor area should also be cleaned on a regular basis to reduce the amount of ambient dirt and dust. To get the best performance from your compressed air system, minimize the contaminants going into your compressor. Choose the right air treatment equipment by carefully examining the air quality requirements of your applications. Develop a maintenance program for your air treatment equipment. A good maintenance program can pay for the equipment through reduced energy costs. The Compressed Air and Gas Institute is comprised of manufacturers of compressed air products and services. They will be happy to answer any further questions you may have about treating your compressed air. The Compressed Air and Gas Institute also offers a wide range of publications on compressed air topics. For a complete listing of all these resources, log on to www.cagi.org.